All right, so the thing about a mixture problem is it starts just as it sounds, as a mixture of something. So if we look at this first example here, we're told that we have a mixture of solid sodium carbonate and solid NaCl. All right, both of these are mixed in a sample. We know the total mass is 0.326. We then take this mixture and we dissolve it in water. I'm sorry, not water, in HCl. And then a reaction takes place and it produces CO2 gas. So the equation that's actually taking place is right here. Right? So here's the sodium carbonate reacts with HCl and it produces sodium chloride, carbon dioxide gas, and water. Now notice that in this mixture, you have two compounds present, sodium carbonate and sodium chloride, yet the reaction only shows sodium carbonate reacting, right? And the result of that reaction is sodium chloride, which tells you that the sodium chloride is inert. It's there, but the sodium chloride is not doing the reacting. It's only the sodium carbonate, okay? The goal of any mixture problem is to find out what the original proportions were. What percentage of the original was the sodium carbonate? What percentage was the sodium chloride? So, with every mixture problem, there's different approaches. In this case, let's take in everything they've told us. They are telling us the volume and molarity of HCl. Well, what do you suppose we could get from that? Yeah, that's moles. The first thing we should do is find out how many moles of HCl had reacted. Okay, so 0.0436 liters times 0.116 molar. Point 0.005058. Okay. So now I know the moles of HCl. That's good. That gets me one step closer. How stoichiometrically useful would be the moles of HCl? What could I do with that number? Yeah, use the mole ratio. Because if I know how much HCl reacted, then I can figure out how many moles that it reacted with. So, 0.005058 moles of HCl. We have a balanced equation already. And what should I solve for? If the goal is to find the percentage of each of those two compounds in our mixture, what could I be solving for here that would be useful? Because we have a balanced equation. There's lots of stuff in that balanced equation, but it's not all pertinent.
You solve for the sodium chloride.
I could solve for the sodium chloride, but if I did that, yeah, well, let's see. No, you can't solve for the sodium chloride because we had sodium chloride to begin with, right? And so that actually wouldn't tell us. That wouldn't actually be helpful. We need to solve for the thing that's actually doing the reacting. Yeah, the carbonate, right? Okay, so the HCl, we can use the HCl to track how much sodium carbonate is reacting. Okay. All right. And now we've pretty much gotten through the crux of the problem. We just kind of have to finish it off as a formality. I know how many moles of sodium carbonate reacted. The question is asking the percent by mass. So what do I do next? Yeah, it's the molar mass, right? So molar mass of sodium carbonate is 106 grams per mole. So we're looking at 0.2681 grams of Na2CO3. And of course, now that we know that, we can subtract that from what the total was to get our mass of sodium chloride. All right, so whoops, nope, 0.0579. 0.058 grams of NaCl. Okay. At this point, we've got the masses of both. To find the percentage, 0.058 over 0.326 times 100%. About 18, it's about 17.8. And your sodium carbonate, we already had that mass. $82.2, which makes sense. All right. This was a straight up stoichiometric mixture. Okay. We were able to get the solution because we tracked one of the reactants. Now, this is all fine and good when only one of the reactants reacts. The other reactant in your mixture was sodium chloride, and that didn't react. That was just kind of there as filler. So, the next example we have a mixture of hydrates, of copper sulfate hydrate and magnesium sulfate hydrate. All right, so just imagine you got a beaker or a crucible or whatever. It's got the two in there. You do know the total mass is 5.020 grams. You do not know the proportions. All right, so here's what they did. They heated the sample, and that results in anhydrous salts. Right? So if copper sulfate hydrate and magnesium sulfate hydrate are heated and it's dehydrated and what's only left is the anhydrous, what that means is you've got CuSO4 and MgSO4. All the water is gone. What is the first thing you can calculate when you look at this?
Mass of the water that's lost.
Right, it's mass of water loss, right? So let's do that. So 5.020 grams total minus the recovered 2.988 grams of anhydrous. .032 grams of water loss. Okay. So, here is the difference from the first example. Both of these components of the mixture are changing. It's not just one. Both of them are. And so since they both are, and we don't know by what amount, we're going to have to use a system to solve this. Now, the first and most obvious system or equation to write in the system for all of these mixture problems is simply the mass of component A plus the mass of component B equals mass total. In this case, X grams CuSO4 dot 5H2O plus Y grams of MgSO4 dot 7H2O equals what the total mass is, which is 5.02 grams. This should be the first equation you look for in your typical mixture problem. Find the sum, find the total. Okay? Now, the other value that's going to be useful to us is the mass of the water that was lost. So, if we know what the total water loss is, 2.032 grams, we can apply X and Y terms to help us solve how much came from each hydrate. And we're going to use this using mole ratios and mass ratios. So I'm going to start by saying, all right, X grams of the CuSO4.7H2O. The first thing I'm going to do is realize, okay, in 1 mole, you know what, this is going to be a lot of writing, so I'm going to shift this as far to the left as possible. I don't want to run out of room. So 1 mole, I need to figure out what that molar mass is of that whole hydrate formula. Okay, so I'm going to add up the copper, 63.55, plus sulfur, 32.07, plus 4 oxygens, which is 64. Okay, so 159.62 plus 7 waters, so plus 7 times 18.02. So this whole formula's molar mass is, whoops, I made a mistake. That's not 7, that's supposed to be 5. Sorry, my bad. Okay. So this whole formula's mass is actually going to be 249.71 grams. Okay. This first step accomplishes turning whatever X grams is into moles. Moles of copper sulfate pentahydrate. But notice that the value that I need to set up and work with is right here. So I need to convert this into terms of water. So the next step would be to stoich this out and say, all right, for every mole of CuSO4.5H2O, there's 5 moles of water within. Canceling the moles of the hydrate compound, now putting this in terms of moles of water. But I need to get this into terms of mass of water. So I go one more step. Mole of water, 18.02 grams. Okay. As far as X is concerned, whatever X is, this stoichiometry will convert this into grams of water. Does that make sense? Okay. So now we have the other compound to deal with. The other compound was issued a value of Y. Now, having 2 variables does not work. Okay. No problem, because I can just rewrite this equation over here. I can just rearrange it and solve for it in terms of X. So Y is equal to 5.02 minus X. Simple algebra. That makes sense? I'm reducing terms. I'm getting out of Y. Now I'm representing Y in terms of X. So 5.020 minus X grams of MgSO4.7H2O. And what I'm going to do is I'm going to stoich this out and put this in terms of water the same way I did for copper sulfate. So I need the molar mass of the magnesium sulfate pentahydrate, which I think I wrote down ahead of time. A mole of this is 246.51 grams. All right, so that's moles of the MgSO4.7H2O. So I need to go to another step and go to moles of water. There's 7 moles of water within. And one more step. A mole of water is 18.02 grams. Okay. And the sum of both the X work and the Y work is equal to what we said the total mass of water loss is. 2.032 grams of water. And now we just have to crunch the numbers. We have our solution. We have assigned X as the mass of the copper sulfate hydrate. So once you solve for this, you do the math, you crunch numbers, you will have the value of X, and that will lead you to what the answer is because they're asking for mass percent. So it would be X over the total mass, which is 5.02. Now, this is where I strongly encourage you just use the solver function so you don't waste like 20 minutes having to like distribute and foil and all that stuff, right? So you guys remember the solver function? If you still need a calculator, you should practice doing this in a calculator, guys. If you come and borrow one here, if you don't have one. You want to practice doing this. You're going to have to know how to do this. So here's what I would do, right? So depending on which calculator you have, if you have an 83 or an 84, first things first, so go to math key, choose the solver function, which is usually 0, but it might not be, right? And so you want to enter in, if you have a new 84 that's got the multiple boxes, this is in box 2. And the algebraic expression for this is all in box 1. So kind of to simplify this, I would enter it this way. Right? So X times 5 times 18.02 divided by 249.71 plus parentheses 5.020 minus X times 7 times 18.02 divided by 246.51. Right? So this all here would be box 1. And then box 2 is just 2.032. Remember that you need to put 0 on the X line after you enter and make sure that you hit alpha when you solve because this is an alpha function. So let me know what you get when you get X. I'll give you a hint. It's between 3 and 4. What'd you get?
I got 3.551.
That's correct. X is 3.551 grams of CuSO4.5H2O. And therefore, your percentage would simply be this over what the total was. And that's going to be 70.8% of the copper sulfate pentahydrate. All right. If you did not get that, I will walk around the room and take a look and see how you entered it right here after I stop this recording.